Okay, so in the last unit, we talked about limits. We talked about one-sided limits. We talked about when the limit existed, when the limit went to infinity. And this unit, we're going to talk about continuity and when a function is discontinuous, what that means about limits, and how we can use limits to help determine the types of discontinuities that we're going to talk about. We're also going to use limits later on to also talk about differentiability and the different types of ways that a function could not be differentiable. So the first thing we need to talk about is what makes something continuous. So in order for a function to be continuous at a given point, the function needs to be defined at that point, the limit needs to exist at that point, and the last piece of the puzzle is that the limit at that point and the function value at that point are the same exact thing. If we are talking about a function that has discontinuity, in particular, we'll start with a removable discontinuity, that would imply that the limit still could exist, the function could still exist, but the limit and the function values do not approach the same thing. So in other words, if we had the limit as x approaches c of the function, and that came out to be, we'll do numbers here. If that came out to be 4, that would imply that f of c is equal to anything other than 4. That would be a removable discontinuity. It could have been 5, it could have been 6, it could have been negative, it could have been non-existent. And I'll show you a picture of what that looks like. Non-removable discontinuities are going to be when the limit itself doesn't exist. So there are 2 types that we're going to focus on, at least that we have special names for. There's others too, oscillating ones, but we're going to focus on the jump discontinuity. So that's when we have a one-sided limit that exists. So if I did the limit as x goes to c from the left, and that came out to be 4, and the limit as x goes to c from the right comes out to be something different, anything other than 4, or any finite value other than 4, perhaps 5, then that would be a jump discontinuity again. I'll show you a picture of that. The last one is going to be when we have one-sided limits that are not finite or are infinite. And so if we did the limit as x goes to c from the left, that one could be going off to infinity, and the limit as x goes to c from the right could be going the opposite direction. And essentially this would be like a vertical asymptote, not negative 8, sorry, negative infinity. And so those are the 3 types of discontinuities we're going to focus on. So graphically, a removable discontinuity, you could see that the limit approaches this value right here. Okay, so we have the limit approaching this value here, but the function value at that point is there. So there's a removable discontinuity. So you could see in this little box here that the limit is defined, the function is defined, however, they do not approach the same thing. Another type of removable discontinuity is, again, the limit is defined, but then the function doesn't even exist at that point. So there's another type of removable discontinuity. We also have jump, right? So like a piecewise function. You can see that the limit from the left is this finite value. The limit from the right is this finite value. And so that one is a discontinuity. It kind of makes sense with the name. If I'm tracing along the curve, I have to jump from here to here to continue tracing. And then an infinite discontinuity is going to be essentially a vertical asymptote. The one-sided limits go to positive and negative infinity. All right, so let's answer a few questions here. First question, determine at what values of x the function have a discontinuity and describe the type of discontinuity. So we have this first one, the function x squared minus 4 over x minus 2. So we could already see that the numerator here, the numerator is going to factor into x plus 2 and x minus 2. Now I'm not going to cross them out because the function does not exist at 2. So if I asked you what's f of 2, we get 0 over 0. So it's undefined. Now 0 over 0 in terms of a limit can be evaluated. So if I do the limit as x approaches 2 of f of x, now when I cross out the x minus 2's, we end up getting 2 plus 2, which is 4. All right, I can just cross these out. I'm going to highlight them so that you can see that I'm kind of visually crossing them out in my head. At least I would cross them out when I'm plugging in the actual rational function inside the limit. All right. So there we have a removable discontinuity at x equals 2. And that's actually the only discontinuity for this one. The next one, I have 3 is where the function is undefined, right? The domain doesn't exist at x equals 3. So now we're going to see what happens if I do the limit as x goes to 3. And when I do that, I'm going to end up with 1 over 0, which tells me that this is a DNE, does not exist, non-existent. So we're going to have an asymptote there at x equals 3. And so this is an infinite discontinuity. More specifically, I could actually address the one-sided limits. The limit as x goes to 3 on the left, well, if I think about 1 over 0, since I'm going to 3 from the left, I'm plugging in numbers slightly less than 3. So this is almost like having a 1 over, I'm going to kind of break a rule here, negative 0. 0 can't be negative. But in reality, I'm kind of saying it's a negative tiny number, which means that this is going to negative infinity. So I'm going to have an asymptote at x equals 3. And this graph is going to actually go down to negative infinity. And if you had to guess, it's probably going to go to positive infinity on the other side. And again, you could do the limit on the other side, and you would see that you're getting a positive infinitesimally small number. So that's an infinite discontinuity. I guess I should graph this function here. For example, x plus 2, and this graph will look like y equals x plus 2. So it's going to be a linear function that goes through y equals, has a y-intercept of 2 and a slope of 1. But when I get to the point 2 comma 4, I'm going to have this little hole there. Right? That's what that graph would actually look like. If you try to use a graphing utility like a calculator or Desmos, you'll see that graph without the hole because it can't kind of capture that idea. All right, so example C. Absolute value of x minus 3 over x minus 3. Well, if I think about all the values, again, this function is undefined at 0. So not 0, at 3, f of 3 is undefined. So we have a discontinuity at x equals 3. The question is, what type? Well, if I think about it as a piecewise function, for all the values to the right of 3, I'm going to end up with positive 1. So if I think about 3, I have a graph that's going to be equal to positive 1. And if I think about values to the left of 3, try to get an open dot here, right? Doesn't exist at that point. I'm going to have a y value of negative 1. And so you could see that this is clearly a jump discontinuity by the graph. The limit as x goes to 3 from the left is equal to negative 1, and the limit as x goes to 3 from the right is positive 1. So we have finite values for those, which is kind of what's giving us our jump discontinuity. Piecewise, most likely going to be another jump discontinuity, but let's just kind of confirm that first. The jump, if we had one, would occur at x equals 1. So let's take the limit as x goes to 1 from the left, and the limit as x goes to 1 from the right of the function f of x. So if I'm doing the limit as x goes to 1 from the left, I'm using the top piece of the function. If I plug in 1 there, 1 plus 2 is 3. And the bottom piece of the function, if I plug in 1, 2 minus 1 is not 3, it is 1. So this is going to be a jump discontinuity. So x plus 2, if I graph that, we already have it actually in part A, right? A line with a slope of 1. And looking like that. And then 2 minus x is going to be a line that looks like that. The other reason I guess I should have known that this is not going to be continuous is even just the fact that f of 1 is undefined, right? Our piecewise function didn't define a value at x equals 1. Notice the inequalities there. All right, x squared plus 1. Well, that's just a simple parabola. Polynomials. Polynomials are smooth, continuous curves. So this is continuous and differentiable, although we weren't asked that, continuous everywhere. The limits exist at any x value I want. I could do any limits I want, and the function value matches that. All right, so the last one we have to talk about here, probably the most interesting, in the fact that we're going to have two different types of discontinuities. The bottom factors into x parentheses x minus 3. So you can see that we have factors that are going to cancel based off of that. So we have one, it's going to be a removable discontinuity if I do the limit as x goes to 0. And if I plug in 0, obviously I get 0 over 0. But if I plug it into the reduced function, the top would become 1, and the bottom is x minus 3, if I plug in 0, is negative 3, so 1 over negative 3. But f of 0 is undefined. Okay, so then we have the limit as x goes to 3. And since I kind of already have an idea that this is an infinite discontinuity, I'm going to do a one-sided limit for this one. Well, we actually already have that up here in part B, don't we? The limit as x goes to 3 from the left is going to be negative infinity. So if I try to graph this function, we have a hole at 0, comma, negative a third, and a vertical asymptote at x equals 3. So we have a removable discontinuity at x equals 0 and an infinite discontinuity at x equals 3. All right, so if I continue to graph this, we're going to get pretty much the same graph as part B, just with an added feature of a hole. I should have I never actually answered part D here. That was a jump discontinuity. And I talked about that. I was pretty sure that that's what it's going to be. Okay, so I tried to get this under 15 minutes, which I barely did. All right.